Welcome to our OpenSim webinar. My name is Jennifer Hicks. I'm the OpenSim project manager, and I'll be serving as the moderator for the webinar today. Today's presenter, Tim Dorn, will describe and demonstrate a plugin that he's developed to perform a muscle-induced acceleration analysis. OpenSim is a freely available software application for visualizing musculoskeletal structures and simulating movements of humans and animals. The application includes tools for general purpose inverse dynamics, optimization to estimate muscle and joint forces, and tools to analyze and visualize the results of simulations. The first goal of our webinar series is to showcase cutting-edge research that's being performed with OpenSim. OpenSim is also a growing and geographically diverse community of users. Thus, the second goal of our webinar series is to provide an easy platform for the OpenSim community to communicate and collaborate. Before we get started, I have a few reminders about the webinar format. Questions will be addressed at the end of the presentation using the Q&A panel. If you need additional technical help, you can also consult the guide on our website. And with that, I'd now like to introduce Tim Dorn. Tim Dorn is a postdoctoral scholar in the Symbios program here at Stanford University by way of Melbourne. He's an expert OpenSim user who has developed plugins and used OpenSim to understand the mechanics and muscle coordination of running.
Okay, thanks, Jen, for the nice introduction, and welcome to those of you who've registered and are viewing this seminar today. So today I'm going to describe a muscle-induced acceleration analysis plugin that I've developed for OpenSim. And this webinar is going to be split up into two main sections. The first, parts 1 and 2, will be more slides-based, and we're going to go over some of the theory and some of the motivation for using induced acceleration analyses. And then in parts 3 and 4, we're going to get our hands a bit dirty and actually use OpenSim to find out the induced acceleration analysis of walking using some real experimental data. Just a reminder before I begin that there'll be plenty of time for questions at the end, and the example that we're going to go through is not designed for you to go through real time. I'm going to go through it quite quickly because of time constraints, so this webinar will be also completely available at the end for you to download and experiment around at your own pace. So some of the motivation for conducting muscle-induced acceleration analyses, and I suppose the best way to motivate this discussion is to start with a very simple example. So we have someone walking here with mass M, and for simplicity we're going to assume that they have a single stance phase, so only one foot is on the ground, and they're going to develop ground reaction forces at the foot. Now, for those of you who know the ground reaction forces for walking, you can split the ground reaction forces up into 3 components: horizontal, vertical, and medial lateral. And these components you can actually measure just on a force plate during a gait experiment. Now, muscles ultimately contribute to these ground reaction forces. So let's say we have a muscle here in red, and that muscle is contracting and developing force. Those forces are going to be transmitted through the joints to the ground, where we will induce a ground reaction force just due to that muscle only. Again, we have another muscle in the body, and that too, as it develops force, will contract and develop force at the ground, and that too will contribute to all 3 components of our ground reaction force. So in theory, if you add up all of these individual muscle components, what you're going to get is the net ground reaction force that you actually measure on a force platform. Now, from Newton's second law of motion, the acceleration of the center of mass of this body is equal to the inverse of the mass of the body multiplied by the ground reaction force. So if you know how an individual muscle contributes to the ground reaction force, you can then work out how that muscle actually accelerates the center of mass of the body. And that's what one definition of what we term muscle function. So muscle-induced acceleration analysis aims to basically decompose the ground reaction force into its individual muscle components to determine how individual muscles accelerate the body center of mass. And this is one way to infer muscle function. So another way, you could also decompose the net joint acceleration of any joint in the body, and you can work out how individual muscles accelerate the joints. But today we're just going to focus on how the muscles make up the ground reaction force, and therefore how the muscles accelerate the center of mass of the body. So what do you need to run a muscle-induced accelerations analysis? Well, first and foremost, you need a model. A musculoskeletal model, which includes segments, body segments, which are connected through articulating joints and actuated by muscles. Secondly, you need some data, some joint kinematics and ground reaction forces. Typically, these are obtained through gait experiments. So motion capture can obtain joint kinematics, and force plates can measure the net ground reaction forces. And with this data, you can actually calculate muscle forces. And OpenSim provides several algorithms that can be used to calculate muscle forces, such as static optimization, computed muscle control. Now we're going to deal with static optimization. It's the simplest method for calculating muscle forces. I don't really want to go into the details of static optimization too much, but essentially what it does is, out of the infinite combination of different muscle forces which could possibly be generated to produce your experimental kinematics, it will pick out one of those solutions according to a specific objective function. And usually the objective function that's used to calculate muscle forces is to minimize the sum of the activations squared across all muscles in the model. So more information about how static optimization works is available in the OpenSim manual. So once you have the muscle forces, the first step is complete. You also need a ground contact model. And I'm going to talk a little bit more about the ground contact model in just a moment. It's a very important part of conducting muscle-induced acceleration analysis because it allows ground reaction forces to be developed inside the model. Once we've got the ground contact model, we have an induced accelerations analysis, and together we can input all of this information, the ground contact model, our muscle forces and our kinematics, and we can calculate muscle contributions to the ground reaction force and or the joint accelerations of the model. Just briefly, what an induced acceleration analysis does is, once it's provided with a list of muscle forces that it's previously calculated, it will loop through and apply each of these muscle forces in isolation and calculate the net effect of that muscle force to the ground reaction force and the joint accelerations in the model itself. Now again, I'm not really going to go through the algorithm because of time constraints of how the induced acceleration analysis actually works. But later on, I'm going to refer you to a user manual which you can find all of that information. Briefly, I'm going to talk about the ground contact model because it is a very important part of the induced accelerations analysis. And we're going to introduce this plugin that I've created. It's called Induced Accelerations PI. Don't worry about what the PI stands for. This is the name I've given to the plugin, and we'll show you examples of how that works in just a moment. So the ground contact model. We have contact occurring at 5 points around the foot, 2 points at the heel, 2 points at the metatarsal joint, and 1 contact point at the toe. And each of these contact points can make and break contact with the ground at different times during the stride cycle. And these contact points have associated kinematic constraints, which define essentially the way that the contact point is in contact with the ground. And these points are able to change during gait. We know that during the gait cycle, we have different contact constraints. So we have a set of rules which define how these contact points actually make and break contact with the ground during the stance phase. You can think of each contact point as a set of 3 springs, where each stiffness of each spring can vary with time. So what I've got here is a schematic. If you're looking down on the sole of the foot, each of their 5 contact points have associated stiffnesses. And the dark circles are associated with infinite stiffness, and the light circles are associated with 0 stiffness. So these 0 stiffness points can come off the ground, whereas the rigid contact points are rigidly connected to the ground. And we have some rules which define how these contact points stiffnesses actually change with respect to this blue dot, which represents our center of pressure, which we record during an experiment. So when you first contact the ground, the center of pressure lies behind the heel, and you have these 2 contact points, these 2 heel contact points, fully constrained, which essentially means that the foot is a hinge joint and it's rotating about the heel axis. Now, as we walk, the center of pressure moves more anteriorly, and what happens as we approach this line, the heel axis, these 2 contact points will stay rigidly connected to the ground. As the center of pressure moves past this heel axis, what's going to happen is our metatarsal contact points are going to gain stiffness, and this is going to happen continuously so that we have continuity in our results and continuity in our contact model. So by the time that the center of pressure reaches the midline of the foot, we're going to have the 2 heel contact points and the 2 metatarsal contact points fully constrained. So the foot essentially now behaves like a weld joint. And this only happens during the mid-stance part of the stance phase, where the center of pressure lies directly in the middle of the foot. As the center of pressure continues to move more anteriorly, what's going to happen is the metatarsal contact points will stay rigidly contacted to the ground, and the heel contact points will slowly lose stiffness, and this will again happen continuously, so that by the time we reach the metatarsal axis, the center of pressure reaches the metatarsal axis, the foot essentially behaves like a hinge joint again, but this time it's rotating about the metatarsal axis. And then finally, as the center of pressure moves towards the toe contact point is going to gain stiffness, and the 2 metatarsal points are going to lose stiffness smoothly again, until we get to the final part of the stance phase, where the foot is essentially acting like a ball joint about the toe contact point. So we've got contact points which change smoothly with time, and therefore our results that we get out of our induced accelerations analysis are also going to be smooth. So this contact model and the induced acceleration analysis together are combined into this plugin, and this plugin is freely available, and I'm going to show you how you can install this plugin into your current implementation or your current installation of OpenSim. Just before we do, plugins are a great functionality of OpenSim because they allow the components of OpenSim to be extended. So you can add, for example, your own muscles. If you have developed a muscle model, you can create that muscle model in the API of OpenSim. You can program that muscle in as a plugin, and then you can actually introduce that muscle into your model. Similarly, you can implement your own controllers into OpenSim, and you can also introduce your own analyses into OpenSim. So this is what I've done, and an induced accelerations analysis is one example of a plugin. So the first thing you want to do if you want to install this particular plugin is you need OpenSim installed. Get the latest version, which is the VC10 build. Go to the OpenSim website, download the latest version of OpenSim. Secondly, you'll need the plugin. So you can go to this website at the top of the screen, and you can download that plugin. Click on the Downloads button, and you'll notice there is a zip file containing that plugin. Make sure that you have the VC10 build of the plugin version, and the OpenSim version must be consistent. So when you extract this zip file, you're going to have two files and a folder. This example folder, we're going to go through this example very shortly, contains all the example files for an experimental trial of walking, and we can perform an induced accelerations analysis on that trial. So we're going to do that in just a moment. Now you'll also have a file here called, well, it's going to be the user manual in PDF format, and I've got a copy of the user manual opened here. You can browse through that in your own time. It contains all of the theory behind the induced accelerations analysis, and it also includes information on the contact model. So you can have a read through that at your own pace. So it does contain quite a lot of information in some detail, which I'm unable to go through in this webinar, so you have that available to you. The most important file of this zip file is the plugin itself, this DLL file. To install it, all you simply do is drag that into the bin folder of where you installed OpenSim. And that's really all there is to it. Assuming that you've installed OpenSim correctly and your paths are all set up, that plugin will become immediately available to you. So to test that this plugin can be actually detected, load up a command prompt window from Windows and type in analyze, which is the analyze tool from OpenSim, -L, which means we want to load an external plugin, and then the name of the plugin. And if everything is set up correctly, you're going to come up with this little bit of text here. It says loaded library int ACPI. And that just means that the plugin DLL file has been detected in your OpenSim folder. Now, don't worry about this little error message you get below. This just means we haven't actually specified a setup file at this point in time. We're not actually running the analysis yet. We just want to check that this analysis can be detected. So in fact, we're going to use the command prompt to execute our analyses, and everything that you do in the graphical interface of OpenSim can be done in the GUI, can be done in the command prompt, sorry. It's going to be done a lot faster if you do it in the command prompt because you don't have to initialize your graphics adapter and you don't have to perform a lot of graphics computations to animate the solution during the analysis. You can simply run it in the command prompt, and then you can animate the solution at the end. So for example, if you want to run an analysis in the GUI, you would go to Tools, Analyze, you would set up your analysis and click Run. Alternatively, you can set up an XML file with all the information that is related to the analysis, and you can execute that analysis from the command prompt. And so we're going to use this right-hand way of doing things during the examples. So this time we've installed the plugin. We know a little bit about why we want to conduct muscle-induced acceleration analyses. So now we're going to use the plugin to perform a muscle-induced acceleration of walking. And we provide an example for you in the examples folder. So again, this is the pipeline that we're going to follow during this example. We've got a model, we've got some kinematics and ground reaction data. We're going to run static optimization to calculate muscle forces. And then once we have the muscle forces, we're going to run the induced accelerations analysis plugin to calculate how these individual muscle forces actually contribute to a ground reaction force. And therefore, we can find out how that muscle will accelerate the body center of mass. So first, we're going to visualize the walking motion in OpenSim. So we'll get out of this presentation, and I'm going to just load. So I have here the example folder, so you can see what sort of files are contained in the example folder. We have our model, our OpenSim model file. We have some setup files for static optimization and our induced accelerations analysis. We have our ground reaction force information, center of pressure information that we've recorded during an experiment, our kinematics. We have some extra geometry for our model. So we're going to load OpenSim and we're going to open this model. So this is very similar to a model that you would find contained with OpenSim. We're going to load in our kinematics that's provided. And one thing you might notice that's a little bit different about this model is that there are actually some marker positions on foot. And these actually form our contact points. So the way that we define our contact points, our 5 contact points on each foot, is by defining them as marker locations. That way we can very easily change and analyze how these contact points actually affect our results, if you would like to do that as a separate study. So you can see we've got our 2 heel points, 2 metatarsal contact points, and our toe point. And I've just loaded in an example of normal walking. Next, we want to run static optimization. So we're going to compute the muscle forces, and as I mentioned before, we're going to do this in the command prompt. So one of the things about loading a command prompt, we want to execute all of our analyses from the directory that we have all of our example files in. So make sure that is the current working folder. To execute a static optimization analysis, we've already got provided our static optimization setup files. So we're going to type analyze. We're going to provide a setup file, and we're going to type in that setup file name. So while that runs, I'm going to open up the setup file itself so you can see the kind of tags that we're including in our setup file. These allow static optimization analysis to run. So this is running in the background. The first thing you have to provide is a model. We've also appended some reserve actuators. Now, I'm not going to go too much into reserve actuators at the moment, but basically information is available in the OpenSim manual. And what they do is they just have specific pure torque actuators applied at each joint in addition to our muscles. So just in case, for example, the muscles are not strong enough to provide a solution for our motion, then these reserve joint actuators will kick in. We have our results directory that store our results in. We have some information about our times that we're going to be running the analysis from. We provide our kinematics and our ground reaction force and center of pressure information. And we're executing an analysis, a static optimization analysis. We're executing these every 5 time intervals, so you can specify how many step intervals you would like to execute this analysis for. So if you had this is 1, for example, you would execute the analysis at every time step. So to make this run a little bit faster, we're going to be executing the analysis at every 5 time steps. The objective function we're using to calculate our muscle forces is to minimize activation squared. So we've got number 2 here as our activation exponent. And all our results are going to adhere to our force length and force velocity curves. So now our static optimization analysis has executed, and it's going to generate our results in our results folder. And if you just have a look in here, there'll be a file called static optimization _force. And this file contains our muscle forces that are required to produce our experimental motion. So now we have our muscle forces. The next step is to now use these muscle forces together with our model and our kinematics and execute the plugin, the Induced Accelerations Analysis plugin, to determine how these muscle forces actually contribute to our ground reaction force. So in a very similar way, we're going to execute this analysis in the command prompt window. We're executing the Analyze tool. We're providing a setup file. This time we're providing the Induced Accelerations Analysis setup file. But because this is a plugin, we also have to load the plugin. Otherwise, we can't run this analysis. OpenSim won't know where to find this analysis from. So we type in the plugin. So we're executing a plugin and we're providing a setup file. So this analysis will then run in the command prompt window. It will be a lot faster than executing in the GUI itself. But I'm just going to minimize this and we'll go into the setup file so we can show you what's in the induced accelerations analysis setup file. And it does look very similar to the static optimization setup file that we saw earlier. So again, we've got model information. We have the same reserve actuators that are appended. A lot of this information should be kept identical to keep our models consistent. So we've got our analysis times that we're setting up, our kinematics, our ground reaction forces and center of pressures. But this time we're running a different analysis. Some of the information that you need to provide this analysis, we've got our center of pressure information, which is contained within our kinetics file. And if you recall from before, our center of pressure is used to determine how the contact points actually are constrained to the ground at different times during the gate cycle. So we need to provide this analysis with a time history of our center of pressure. We've also got our muscle forces, which are important. We need to provide this information so that the analysis can loop through each of these muscle forces and apply them in isolation to calculate the effect of each muscle force to the ground reaction force. I've got some other information here which I'm not going to go through, but all this information is included in the user manual for this analysis. Actually, one of the very important parameters you need to put is the foot point markers. Now, if we looked at our example here before, I showed you that our contact points are actually set up through marker positions. So the names of these marker positions here you can see on the left are included in this tag. So we can specify the names of our marker locations which correspond to our contact points. So now our analysis has run, and we'll have a folder created here with our results. And I'm going to open up this folder. There'll be lots of files. Don't be intimidated by the number of files in here. There's a lot of information contained in this results folder. But every single joint in the model will have its own file. And if you open up this file, you can see how the muscles actually contribute to this joint's acceleration. Similarly, there'll be some ground reaction force files. So if you want to know how any muscle in the model contributes to any of these ground reaction forces, X, Y, and Z, for the left or right foot, we've got that information contained within this file, these files as well. So I've got a lot of information here. Now it's time to really go through this information and try and answer some questions. So let's investigate the outputs of this analysis, see what information it can give us. I suppose before we look at the results, we would like to have some sort of idea as to how valid our results actually are. So one of the big questions from induced accelerations analysis is, how do we actually check the solution that we've got for validity? So you might recall that as each muscle contracts, develops force, that force will be transmitted through the joints to the ground, and each muscle will produce its own little component to the ground reaction force. And in theory, if you add up all of these components, you should get the net ground reaction force here in gray, which is what you measure on the force plate during an experiment. So our results should at least satisfy the principle of superposition. But sometimes that doesn't always happen. You get a superposition error, which means your experimental ground reaction force here in gray is a little bit different to what your ground contact model calculates when you add up all the muscle contributions to the ground reaction force. And ideally, you want this superposition error to be as low as possible. Or in other words, you want the experimental ground reaction force to match the model computed ground reaction force as closely as possible. Now, this is one way you can test that your results actually have some sort of meaning, but it doesn't mean that just because superposition principle is satisfied that your results are going to be correct. And this is actually one of the big outstanding problems in biomechanics, is that we can't actually measure experimentally how one individual muscle actually contributes to a ground reaction force. But at the very least, our models should, our solutions should satisfy the principle of superposition. So what we can do is load up our plotter, and we can plot some of our results. Let's load in some of our results. So we're going to look at the left foot. Let's look at the vertical ground reaction force for our left foot, as specified in this file here. We can plot, if we go down, we've got some tags here, we can plot our experimental ground reaction force, and we can plot our model ground reaction force, and we can also plot our superposition error, which is defined by this inertial component. And these three outputs, these three components are actually output in all of our files. We'll plot that with time. And here you can see our experimental ground reaction force in green, our model computed ground reaction force in blue, and our superposition error in red. And that's for the vertical direction. Now, the match is pretty good. Again, we can also plot the same information, but for the horizontal direction, for example, our anterior-posterior direction, which is our x direction. So we're going to plot our ground reaction force information for the x direction for our left foot. We're going to go down. We can also plot how individual muscles contribute down here, each muscle in the model. But for now, we're just going to plot our experimental, our model, and our superposition error, just so we can have a bit of confidence that our results have some sort of meaning. So again, here we have our experimental ground reaction force in green, our model ground reaction force in blue, and our superposition error in red. You might notice that we do have some superposition error occurring at the start of stand phase. And so what that means is that we have a little bit of inconsistency between our contact model and our experimental data between these points. And that can happen sometimes because, for example, when you strike the ground, when you impact the ground, you might have some vertical translation due to the compression in the foot. And that's not really taken into account in our contact model. But at the very least, we can see the blue and green lines are matching somewhat, so we can have some sort of confidence in the results that we have. So we can proceed to another question to actually look at a specific muscle. And the question that I've posed is, to what extent does the soleus muscle, one of our calf muscles, how does that muscle support and progress the body forwards during stance? So again, what we can do is we can plot that information using the plotting tool. I'll get rid of the experimental and the inertial. I'm going to add the soleus muscle to this list. We can plot. Let's add that. I'll do the same thing for the horizontal direction. I'll add the soleus muscle so we can see how this muscle contributes to the ground reaction force. So what we can see here is we have our experimental or our model ground reaction force in red for both the vertical in the top and the horizontal directions, and our soleus contribution to that ground reaction force in the blue. So what you can see is that in the vertical direction, the soleus doesn't really do much in terms of supporting the body in the first half of stance, and then in the second half of stance will really come up and contribute a lot to vertical support during walking. Similarly, in the horizontal direction, the soleus actually decelerates the body a little bit in the first half of stance, and then in late stance will really come up and propel the body forward. And we can plot all of our muscles, and we know that if we add up all of these muscle contributions, we're going to get this red line. Now, also what you can do, we can load in a motion. In addition to these ground reaction force files, we have these GUI files, and each muscle has a GUI file, and this GUI stands for Graphical User Interface. And we can actually load this into the OpenSim GUI and see how an individual muscle contributes to the ground reaction force. So if you look through these GUI files and we find the soleus, left soleus muscle, we can actually plot and zoom in now. How each contact point is producing force for this particular muscle. So what we can see here on the left is that there's not a lot of soleus contribution to the ground reaction force occurring until about the late stance part of the stance phase. So as we move forward, we can see each contact point slowly developing some ground reaction force. And at about this point here, we've got peak vertical contribution from our soleus muscle. And that's represented by this graphics here on the right-hand side. We can see as we continue progressing through, eventually the net vector of this ground reaction force contribution from soleus is going to really propel the body forward. So you can actually visualize the contribution of each muscle and how that muscle contributes to each force from each contact point during the gait cycle. Graphically here, as you can see on the right-hand side, and also you can plot this information in the plotting tool on the left-hand side. So we can answer how each muscle actually accelerates the center of mass using these files that we've output from this plugin. So in summary, what we've done in the last 40 minutes is we've introduced a plugin that's being used to extend the functionality of OpenSim. We've introduced a ground contact model where contact takes place at multiple points around the foot. We've showed you how to install a plugin into OpenSim, and we've applied this tool to a real-life example of walking. We've performed some basic validation on the results. We've checked that superposition principle applies, so our results have a physiological meaning. And then we've gone on to answer some basic questions about how specific muscles in the lower limb, how they function during walking, during the stance phase of walking. I'll just remind you that all of these examples that we've gone through, as well as the slides and the webinar, are available, will be made available after this webinar. So you can download the webinar, you can go through the examples at your own pace. You've got the user manuals there to help you through. And you can hopefully have some luck producing your own simulations with your own experimental data using this plugin. So with that, I would also like to acknowledge our collaborators at Melbourne University who helped me develop this plugin. And with that, I'm going to pass it back on to Jen. We can have some time for questions. If you've got any questions, feel free to ask them.
All right, thank you, Tim, for a great talk. Before we start the open question and answer session, I have a couple quick announcements. First, please fill out the survey that's going to appear in a pop-up window when you exit the event after the Q&A session. This will help us improve future webinars. We'll also make a recording of the webinar available on our website, and you'll get a follow-up email that has a link to that, as well as a link to Tim's project with the other materials. OpenSim and this webinar series are supported by several grants from the NIH and EU, including an NIH grant that funds our National Center for Simulation and Rehabilitation Research. Information about the center, upcoming events, and other resources for the OpenSim community are available at our website. And now let's get started with the Q&A session. All of the questions will be text-based. Go to the Q&A box, which will be either at the top or the bottom right of your screen to access that. Type in your question and make sure you select to ask to all panelists, and we'll get to as many questions as possible. So go ahead and start sending in your questions, and Tim will be happy to answer them. I don't see any more questions coming in, so I guess I'll start with a question. You did talk a little bit about the details of your contact model. You did talk a little bit about the details of your contact model. Would you have selected a different model if you've been modeling a different motion, for example?
Yeah, the contact model is very sensitive to what sort of task you're performing. For example, if you were looking at walking or running, you wouldn't want to use a pure ball contact model or a pure weld contact model. Whereas if you were simply just crouching down and performing a small simulation of just a simple crouch, then we know that our foot would be pretty much welded to the ground during that task. So one of the tough things about choosing your contact model is that the constraints that the contact model have should somewhat be defined with respect to the task that you're trying to simulate. So in the contact model that I've specified in this plugin, what we've tried to do is make the contact model variable so that depending on where your center of pressure is, the contact model, the constraints for each contact point actually try and adjust themselves according to what the foot is actually doing. Because we know that the contact points actually change with time. You can make contact with the ground in many different ways. So I suppose one of the advantages of using this contact model, which is included in the plugin, is that the points adapt based on the location of your center of pressure, which is dependent on which task you're actually performing during your experiment.
Okay, so now we have a related question from Andrew Lewis. How are the positions of the foot contact points chosen?
Andrew, that is a good question, and that is actually a design variable. So the way that I've implemented the contact points is that you are free to choose where you want to put these contact points. In a very similar way that you can choose where you put marker positions on a model, you can choose where you want to put these contact points. Now, there are a couple of ways to choose them. One is to look at the geometry of the OpenSim, or the OpenSim geometry, and place them based on that. That's one possibility. There's no right and wrong answer, but what I tend to do sometimes is to look at a trial, look at where your ground reaction force starts and ends in terms of the anterior-posterior distance of the foot, and you can make decisions based on that. So, for example, where the ground reaction force ends, if the ground reaction force ends here or here on your trial, that's usually a good place to put your toe contact point. Obviously, if you want to be really rigorous, you can actually place markers where you think will place markers on the foot during an experiment that line up the heel and line up the metatarsal axis, and you can use experimentally recorded contact points from motion capture. So you're free to choose whichever way you want to put your contact points. And I suppose one of the innovations of this plugin is you have that choice to be made.
Okay, now we have a question from Yusuke Okita. I apologize if I mispronounced that. He wonders if there's a case or cases where static optimization is better than CMC when estimating muscle forces for an IA. So what are the trade-offs and reasons for choosing one versus the other?
So yeah, there's a few different reasons why you might choose CMC or static optimization to produce your muscle forces. It's hard for me to elaborate which cases you would use which algorithm for, but static optimization is fairly robust and it's commonly used throughout the literature. There are limitations of CMC in regards to that it doesn't include activation dynamics, and you can't include time-dependent dynamics
in static
optimization, whereas using a CMC simulation you can. Both of these algorithms, the main purpose is to calculate the muscle forces, and you do need muscle forces to proceed to an induced acceleration analysis to work out how these muscle forces contribute. It's hard for me to answer that question specifically because it does depend on your task, how ballistic your movement is, and the robustness for static optimization and the speed of execution make it very easy and simple to use in an example situation like this.
Okay. Next, we have a question from Bruce Larson. Why would the sum of muscle contributions not equal the ground reaction force when you use the ground reaction force to estimate the muscle contributions in the first place?
That's also a good question. We're using the ground reaction force to calculate our muscle forces, but we're not actually using the ground reaction force in our induced accelerations analysis. What we're doing, instead of prescribing the ground reaction force, which is what we do to calculate our muscle forces, we have a contact model which allows ground reaction forces to be developed. So if we look at this slide here, we're now inputting a ground reaction force into the induced accelerations analysis, and that is replacing the direct input of ground reaction force which occurs into static optimization. So if your ground reaction force, for example, if your contact model is not consistent with the way that your foot is moving during your experiment, you can have some superposition errors. And the superposition error, what I like to think the superposition error, it's just an inconsistency between your ground contact model and the dynamics and the kinematics of how your foot moves during the experiment. So if you have a perfect contact model and perfect set of foot kinematics, then you're going to get perfect superposition, zero superposition error. But if you have, for example, a very bad contact model, let's say you're trying to use a weld joint, pure weld joint throughout the whole stance phase of walking, that's not really representative of how we walk. And the weld joint really does not allow any rotation of the foot or any translation of the foot. So this restriction by implementing a weld joint will cause superposition errors to occur because we actually have rotations and translations of the foot during our experiment. So superposition error can be basically seen as a level of inconsistency between your foot contact model and your experimental foot kinematics.
Okay, now we have another question about the contact model from Andrew Lewis. Do you need to select a custom set of contact points for every set of gait data that you're analyzing, even, for example, if you have two walks from the same subject?
In my opinion, the answer is no, you don't. So I've previously analyzed different running trials from different subjects running at different speeds using the same set of contact points across all speeds and across all subjects. And what I've found in my personal experience is, although contact points can very subtly influence your results, it's more the kinematic constraints which really have the big effect on how the muscles contribute to the ground reaction force. If you're interested on a lot of the sensitivity information about how contact points and how different kinematic constraints affect your results, there's a paper here that's in press that I wrote last year, and that compares a lot of different contact models and different contact points to see how during a walking trial and a running trial, how your results can actually be affected. So you can have a read of that. But in my opinion, if you just subtly change the contact points, you won't get a huge difference in the results. It's more the kinematic constraints themselves which have the major effect on your induced acceleration results.
I have another question about validation. So getting superposition to be correct is a necessary condition for validating, but there still could be other problems. How else do you verify and validate that your results are correct?
Right, so that's actually an open question. The real answer is we don't 100% know. And the reason is because we can't really measure the direct contribution of a particular muscle to the ground reaction force. We just simply cannot measure it. It's impossible to measure. All we can do is measure the net ground reaction force. So while we can check superposition error, and if superposition error is sufficiently low, where sufficiently low is a very subjective term, but if the experimental ground reaction force and model ground reaction force match, you can't 100% say that your results are correct. And that's because you can have different ways of having kinematic constraints between the foot and the ground, which can still get you the same low superposition error. So as untechnical as this answer sounds, it's you have to really have confidence in your contact model, and you have to have confidence in how your kinematic constraints vary to really have confidence in your solution. And so this is an open question in biomechanics.
Well, what about muscle forces? Did you compare the activations to any EMG data from the experimental setup or from the literature?
Yeah, absolutely. So you would compare, at least temporally, with time, the activations of your experiment with the activations produced when you calculate muscle forces, and if they match, at least qualitatively, you can have some confidence in the muscle force that you have. But again, you can't really measure directly. It's very difficult to measure muscle forces in vivo. In fact, you can't do it non-invasively. So again, you have to have confidence in your musculoskeletal model to have confidence in your final results.
Yeah, that was a hard question I asked. Now we have time for some more questions, so go ahead and send them in if you still have them. We have another question from Andrew Lewis about the contact points. Will they move appropriately when you scale a model?
It depends if you allow them to be scaled. So to scale something, you have to provide either a scaling factor or you have to provide some experimental information. So if you record, for example, the contact points on an experimental subject, then you can scale them. If you haven't actually placed any markers on your subject's foot that correspond to these marker locations, then it makes it a little bit harder for you to scale the contact points. But absolutely, if you want to scale them, you can scale them in exactly the same way that you scale markers during a scale tool execution in OpenSim. Just treat the contact point just like another marker in the marker set.
All right. I guess if there are no further questions, we'll go ahead and wrap up. Thank you for everyone for a great discussion, and thank you, Tim. Again, in closing, we ask that you complete the short survey that will appear in a pop-up window. This will help us improve the webinars and choose future topics for webinars. So thank you all for participating, and we hope you'll continue to stay involved with OpenSim.